In this lecture, we describe what happens to a couple of hyperbolas when the reciprocal map is applied to the points on each hyperbola. We designate the reciprocal map as uppercase R of z, where R of z equals 1 over z. The hyperbolas that we will work on are given by the equations 4xy equals 1 and x squared over a squared minus y squared over b squared equals 1, where a and b are positive real numbers. For this exercise, we consider the extended complex plane as both the domain and the range of the reciprocal map, so that r of 0 is infinity and r of infinity is 0. Therefore, the origin is on the reciprocal map image of each hyperbola, since z tends to infinity in 4 different directions on each hyperbola. Let z prime be equal to r of z. The equation of each hyperbola is of the form f of z equals some real valued constant k. Our objective is to transform this equation into the form g of z prime equals some real valued constant k prime. That is, we will obtain an equivalent equation for each hyperbola, but using z prime coordinates, whether it's Cartesian or polar coordinates. Let's work on the first hyperbola for xy equals 1. Let z be equal to x plus y times I, where x and y are real numbers. Let an argument of z be theta, and let the absolute value of z be lowercase r. Let an argument of z prime be theta prime, and let the absolute value of z prime be r prime. And so z equals its absolute value, or r, times e raised to the power I times theta, so that x equals r times cosine theta, and y equals r times sine theta. Z prime is the reciprocal of z, so that z prime equals 1 over r times e raised to the power minus I times theta. Taking the absolute value of everything, the absolute value of z prime should be equal to the absolute value of 1 over r, which is 1 over r, times the absolute value of e raised to the power minus I times theta. Now, the absolute value of e raised to the power I times any real valued angle, positive or negative, is always equal to 1. Therefore, the absolute value of z prime is 1 over r, and so r prime, which is the absolute value of z prime, equals 1 over r. This is a fact that some of us probably already had known, that the absolute values of reciprocals of non-zero complex numbers are reciprocals of each other. So, with 1 over r equal to r prime, z prime equals r prime times the quantity cosine of minus theta plus I times sine of minus theta. And we can set theta prime, or the argument of z prime, equal to minus theta. In the equation for xy equals 1, we replace x by its polar equivalent r times cosine theta, and y by its polar equivalent r times sine theta, to get 4r squared times cosine theta times sine theta equals 1. R squared equals 1 over r prime squared, and theta equals minus theta prime. This equation now involves only coordinates of z prime and is therefore of the form g of z prime equals k prime. Cosine of minus theta prime is cosine theta prime. Sine of minus theta prime is minus sine theta prime. Therefore, minus 4 times cosine theta prime times sine theta prime equals r prime squared. Cosine theta prime times sine theta prime equals 1/2 times sine of 2 theta prime, so that minus 2 times sine of 2 theta prime equals r prime squared. This equation is that of a lemniscate with as axes of symmetry the line x equals y and the line x equals minus y. Let's work on the second hyperbola, whose equation this time is x squared over a squared minus y squared over b squared equals 1. We can still use polar coordinates, but instead we will use Cartesian or rectangular coordinates. We leave it as an exercise for the viewer to try polar coordinates to get the same result. Let z prime be equal to x prime plus y prime times I, where x prime and y prime are real numbers. Z prime, or 1 over z, or 1 over the quantity x plus y times I, equals x minus y times I all over the quantity x squared plus y squared, so that x prime equals x over the quantity x squared plus y squared, and y prime equals minus y over the quantity x squared plus y squared. Because z prime equals 1 over z and z equals 1 over z prime, these equations are symmetric in the sense that x equals x prime over the quantity x prime squared plus y prime squared, and y equals minus y prime over the quantity x prime squared plus y prime squared. All we did was to move the primes from one side of the equation to the other side of the equation. We transformed the equation of the hyperbola by replacing x with its counterpart in terms of x prime and y prime. And do the same for y. We multiply everything by the quantity x prime squared plus y prime squared to get this equation. Or this equation where we have a quartic polynomial on one side of the equation and 0 on the other side. The graph of the 0 points of this quartic polynomial is a lemniscate with axes of symmetry, this time the real axis and the imaginary axis. We now take a look at the graph of each lemniscate as generated by its hyperbola pre-image. Here is the graph of 4xy equals 1 with an arbitrary point z on the hyperbola. Remember that we regard complex numbers as points on the complex plane. We let z travel along the hyperbola while at the same time we keep a trace on the path that 1 over z generates. So here's the lemniscate that's the image of 4xy equals 1 under the reciprocal map, with its axes of symmetry the lines x equals y and x equals minus y. Now we apply the reciprocal map to, this time, the hyperbola x squared over a squared minus y squared over b squared equals 1. For the sake of example, we take a squared equal to 1/4 and b squared equal to 1, so that the equation of the hyperbola shown on screen is 4x squared minus y squared equals 1. We again let z move along the hyperbola and keep a trace on the path of 1 over z. We get a lemniscate with, this time, the real axis and the imaginary axis as the axes of symmetry.